Whoa. Hang on. Push the wrong button. 5, all off. 6 is supposed to be what I wanted. All right. Welcome, everybody. We got pretty close to getting through all of Chapter 4 material on Monday. There's a handful of bacteria we want to talk about briefly, and then we're going to talk about a few archaea just to give us some couple of examples with them. And then we'll transition over and think about some eukaryotic organisms. There are kind of a boatload of different eukaryotic pathogens that we want to at least give a kind of brief introduction to as we move through these preliminary chapters. So any questions before I jump into this stuff? Something on the chat. Okay. So I left off, we didn't talk about Clostridium. I left off right here with Clostridium difficile. This is a type of bacteria that we pretty much all have it in our intestines, but we don't see it usually, don't see it causing problems with us unless we've set the stage for some of our, the majority of our good guys that are there to kind of get depleted, and it allows for the Clostridium to shift gears and to take over. All right. So little bit of them, I guess we could maybe say they might be classified as some good guys as well. They're held in check, but they're part of the normal flora. All right. But when the populations get shifted in their favor, it sets the stage for some potentially very serious ill effects. All right. Sometimes they call Clostridium difficile C. diff, kind of abbreviating stuff like saying Staph aureus, but we abbreviate the difficile as well. And part of the difficile, these suckers are super difficult to deal with in the first place. To try to combat them, to try to treat and rid yourself of these problems, well, it's kind of an issue in the first place because it's something you already had, right? So you need to get the good guys back in a higher population and bring these down to lower levels is really what we're hoping for, all right? So oftentimes it's antibiotics that might set the stage for Clostridium difficile to get a leg up. And we've talked a little bit and we'll talk more about it, but there's all sorts of different types of antibiotics. And the antibiotics that we think about maybe being more of an issue are what we classify as broad spectrum antibiotics. These are the drugs that kind of have a kill 'em all approach, wiping out all sorts of different types of bacteria, gram positives and gram negatives alike. All right. Well, Clostridium difficile happens to be a type of bacteria that has quite a bit of resistance potentials within its genome. It's got the abilities to survive all sorts of different types of drugs that we might throw into our system. All right. A lot of times when we think about these antibiotic issues, it's not some sort of GI problem that you're taking the antibiotics for in the first place. It's some other problem, all right? Some other infection. And you're taking these broad spectrum drugs that in turn does a number on you. And we've mentioned, and we'll mention as we bump over into the next chapter, there are potentials for things like yeast infections with antibiotics, wiping out some of the bacterial populations, lending to those yeast cells proliferating. This is just another bacteria that's able to persist, and it grows out of proportions, all right? And in the intestines, getting a huge population of these bacteria is a problem, all right? It results in some serious issues. You might think that it's killing you, and deep down, it truly could be, all right? It can cause some severe colitis, potentially ulcerative colitis. Colitis is inflammation of your intestines, inflammatory responses, all sorts of things can initiate inflammation. A little bit of inflammation might not be super terrible, but some severe inflammation that can cause some greater impacts, right? Oftentimes, copious amounts of diarrhea, you've got some serious ill effects, right? And potentially thinking you're crapping yourself to death, right? There are opportunities to treat with some other antibiotics that are really pretty harsh, oftentimes causing some ill effects on you, but you're already having pretty ill effects, all right? So maybe, all right? There are some other potentials, and it may seem a little disgusting, maybe like 9 o'clock in the morning. Should we really be talking about that type of stuff? But we're going to, right? So this is a sidebar, but every year as faculty, we have to do like end of the year evaluations and talk about things that we've done, different things in the classroom or whatever it might be. And in turn, we also need to incorporate some student feedback, the end of the semester evaluations. After all of the grades get submitted, that's when we get access to see that stuff. And at the start of the new year, the spring semester, is when all of these things get kind of compiled and looked at, all right? So as I was going through some of those reviews, one of them that made me laugh was coming out of microbiology class, and somebody's comment at the end was, "I have never known someone so excited to talk about bacteria at 9 o'clock in the morning," right? And I was like, hell yes, that makes me feel good, right? So super excited for this, maybe not, right? There are potentials where people have some bad infections with Clostridium difficile, and it warrants a fecal transplant. They get it from someone else, right? Probably some relative, all right? Probably aren't just going to find someone off the street and say, "Hey, can I have a little of your poo?" Right? Probably not, right? Probably some relatives would still hang up the phone. They're like, "No, right? Don't talk to me about this nonsense," all right? But it technically can be very effective, all right? Giving the person that's infected, that's had their good guys depleted considerably, all of a sudden they get somebody else's good guys, right? And we're just really trying to bring our population of good guys back to the level that will keep these in check, right? So getting some of that stuff can be a huge benefit, all right? We're not talking like eating poop sandwiches, all right? There are multiple mechanisms that we get it in your back end, all right? All sorts of different opportunities with this come into play when we think a little bit, and we talked briefly about like the Human Microbiome Project, looking at all sorts of different organisms that we've got on us and in us. We think, some stuff like, well, you are what you eat, right? Well, maybe what you're eating is dictated by some of the microbes in your gut, all right? So through the course of time doing some of these transplants, we have recognized some stuff that I think is flat out awesome, all right? There are some people that need these transplants, and we can think the opposite as well, all right? There are some people that need this fecal transplant that are overweight or obese, and the person that gives them the sample happens to not be, all right? They are within the normal weight range, all right? And in turn, that person that received the transplant, when they start feeling better, they actually drop the pounds because they've got some of these good bacteria in there that maybe initially those populations weren't the same in their gut, all right? And maybe some of the diet that these people were consuming has also shifted the littlest bit, all right? Lending to some weight loss, all right? And we've seen the opposite in a person that we would maybe describe as normal weight, and they receive a transplant from someone that is obese. And then after they have got their populations back under control, if you will, the pounds start coming on, all right? And they gain quite a bit of weight, all right? And potentially, again, you know, I don't have all of this data looking at what did you eat for breakfast? What did you have for dinner, right? With all of these different people. But I think there are some shifts in some of what you may now have some desires to potentially be consuming in the first place, all right? Kind of crazy, all right? I'm not saying that a fecal transplant could be some magic weight loss solution, but it sure makes you stop and wonder, could it be, right? Could it actually be? And then you start looking around and you're like, what I need to do is find the slimmest person, right? I'm going to become friends with them, right? And then I'm going to see if maybe they'll share a little poo, right? I don't know. Could be a pretty good way to lose a friend, right? But if they give you some of that, I'd say you got a friend for life, right? Deep down, you probably do, all right? Crazy, all right? There are all sorts of other things we could think about of, you know, maybe some potential grossness in medicine that we may be employing. And really, when it comes right down to it, a fecal transplant's maybe not that bad of an idea, all right? Kind of crazy, all right? That should be a pack-back poll question. How many would get a fecal transplant if they truly needed one, right? Or would you just say, you know, I'm just going to try these antibiotics, right? What would I do, right? Kind of crazy. All right. So shifting over, we've got an image of Streptococcus pyogenes, the culprit for strep throat. We've got it gram stained, and we also have an image where it's growing on a blood agar plate. So I described these before, Petri dishes that have the blood added to the agar as it's starting to cool, and those red cells are intact. Streptococcus pyogenes is a type of bacteria that we describe as beta hemolytic, all right? It's got the ability to feed on, to destroy those red blood cells. It loves them, all right? And in a blood agar plate, it clears them, it lyses them and sucks up all of the juices, if you will, leaving behind a clearing in that media. The blood agar plates are solid red. If you held them up to the light to look through them, you couldn't. They are opaque, all right? But as the bacteria destroys those red cells, it completely clears it away, and it looks like a nutrient agar plate. You've seen those in the lab already, I believe, kind of yellowish looking, right? And as we see here, there's a lot of yellow and a little bit of red all throughout. Individual colonies growing on the plate. We can see this zone of lysis, hemolysis around the bacteria. And where there's a huge swath of the bacteria, it's basically cleared almost all of it, all right? Oftentimes, trying to cultivate Streptococcus pyogenes, it likes oxygen, but it likes kind of a little bit less than just atmospheric oxygen deep down. You're like, but wait a minute, it's growing in my mouth, right? There's still some potentials for it to be a little less. There's all sorts of anaerobic bacteria in your mouth as well, all right? So the Streptococcus pyogenes, if you're truly in a lab trying to get these guys to grow up real well, what we're looking at here is some streaking for isolation, where we spread the bacteria out in some repeated movements over the plate, flaming the loop in between these steps to basically dilute it or thin it out, all right? And after I've done my very last streaking and I haven't flamed my loop, I still have the hint of some bacteria on my loop. I'm going to take it and poke it into the plate a couple of times, all right? Just right down into it. And that creates an environment for some of those bacteria to have a little bit less oxygen, a little more anaerobic. And sometimes It's just that little poking that's really what shows up on the plate, and the rest of it doesn't grow very well, right? But you get a big clearing, and then you're able to go in and potentially do some more with it if you can get it to grow, right? There are lots of other things like rapid strep tests. If you think you've got strep throat, you go to the clinic, they swab your throat, and in a matter of minutes, truly, they get the results. You may not get those results in minutes, but it only takes a few seconds for these reagents to get mixed, added to the little cassette. And as it moves across, if you have strep throat, you're going to get an indication like a pregnancy test or other types of solid phase indicators like that. All right. They oftentimes will do some cultivation as well. All right. Because sometimes your test shows up negative. Maybe you don't have enough of the bacteria for those antigens to be extracted as you swab the back of the throat for it to actually show up. Maybe if you went back the following day, there would be, right? But by doing some cultivation instead of just rapid strep test, you've got a greater opportunity like this plate, all right, to actually see it. We were to take some of it off and gram stain it up. You can see gram-positive cocci, and these bacteria grow in big long chains, or as they replicate and split in half, basically forming these chains. The strep is a chain, and these guys long chains of bacteria, right? There are others like Streptococcus pneumoniae, not beta hemolytic, right? It's alpha, it's a partial lysis, but not complete clearing, right? And they're little diplococci, 2 of them, and they'd be all over in little doublets, right? There are a few things that may clue us in to some of that stuff, like some antibiotic susceptibility, so they can kill them, or resistance, all right? We won't go through great details with this now, but there is one that ultimately allows us to see that it's pyogenes, and the other would be pneumoniae. Both of these suckers could be growing in the back of your throat, all right? And in turn, maybe recognizing what's really up, all right? So this image, we've got a mixed culture that we're looking at under the gram stain. We've got some gram-positive bacillus and some gram-negative bacillus, or rods, all right? So the gram-negative ones, the pinkish ones are E. coli, and the darker looking ones, this looks more black to me, but purplish is how they really should be appearing. Those are the bacillus, Bacillus cereus and Escherichia coli, all right? On the Petri dish over here, well, this is a culture of Bacillus cereus, all right? It could potentially have both, all right? But really it's saying, it's saying this is just Bacillus cereus, all right? Oftentimes trying to streak things out and get isolation, if we had a mixed culture like this, you might be able to put it onto a Petri dish and get some individual colonies that are distinct from one another, that allow you to say, and maybe through some more gram staining, but allow you to say, this is this type of bacterium and that one is the other, all right? Bacillus, lots of bacillus grow very rapidly and spread out all over the place. We call them swarmers as they just spread. And if you allow this to incubate a little bit longer than maybe you should have, there are opportunities for it to completely overwhelm the other bacteria that were maybe growing on the plate. And you roll in there the following day and look at it, and all you see are these guys, but hiding underneath maybe are some E. coli, right? So kind of just depends on the circumstances and what you've got in that tube as far as how easy it might be to isolate it, right? Oftentimes in a mixed culture situation, it's not just a simple plating a separated amount. You in turn pick some things that you think look distinct, and you do another round of streaking for isolation, replating them out, hoping to get them further isolated to what we would say are pure colonies. It's only bacillus or it's only E. coli, right? Either way. And then we might go through and do some other testing, which is stuff we'll start looking at in the lab soon. So this image, electron micrograph, this one is some Staph aureus. And here we've colored them up and they look kind of yellowish. I would have preferred if we gave them some purple because they are gram-positive. But what we're really looking at are these coccus bacteria that are all clustered opposed to the chains with this gram stain, right? And Staphylococcus, we will talk lots of details about staph, and you'll see quite a few examples of it in the lab. It's a pretty common bacteria, either aureus or epidermidis, both of which you'll see kind of throughout, and lots of E. coli too. Not at ISU, you're not going to see these guys, all right? We'll play with tuberculosis, right? There are a handful of bacteria that we just flat out say, no, right? That's something that truly should be left to the professionals, all right? And in turn, at ISU, we don't have laboratories set up to truly manage dealing with pathogens of this caliber, all right? We just don't play with that stuff, all right? There are some mycobacteria, close cousins, if you will, that are non-pathogenic that we potentially utilize. But we have seen over the course of some years of trying to work with them that they really don't perform quite like we would like them to in the first place. So we kind of don't use them too much. You might see a little bit of it in the lab, not tuberculosis, but some of these acid-fast bacilli, most of it's just going to kind of be talked about, right? Mycobacteria with that mycolic acid layer in the outside of their cell wall makes them kind of waterproofed, kind of protected from lots of stuff, and makes it so that they don't pick up the gram stain very easily. And in turn, it also causes some issues as we think about their replication. They're pretty slow because they're trying to grow and synthesize all of the components that they need to truly survive. It takes more time than like our little staph or E. coli that replicates super fast, right? These could take weeks to double, all right? From one cell to two, right? That's a huge issue, all right? Super slow grower. And if you weren't a patient person, you might look at this 2 days later and say there's absolutely nothing and throw it away, all right? But if you have the hints that it's tuberculosis, you better not do that, right? You need to keep it incubating, and you need to keep it incubating for a prolonged period of time to actually get something that shows up, right? We diagnose tuberculosis through acid-fast staining, and then we get antibiotic susceptibility profiles by cultivating it up, but that typically takes a couple of weeks after we've made the diagnosis before we actually say, this is really the drug we should have been giving you, and we typically shift it up. Maybe not, maybe we picked the right one initially, but the odds are you're going to manipulate some stuff, all right? So these guys, they kind of look like cauliflower growing on the surface of this plate with butter all over the top of them, so that cauliflower tastes good, right? Anything slathered in butter is going to be good. So these colonies, kind of cauliflower looking, raised up colonies on the media. This type of media is a specialized medium called Lowenstein-Jensen that is selective for our tuberculosis bacteria. It inhibits lots of other things and really makes it so it's just these guys growing. That's important when we think about prolonged incubation, right? You want to ensure that there's not something else that's potentially going to take over and grow all over the place like that bacillus did, right? You just want these guys growing, right? There are others like leprosy or Hansen's disease, which is what they would like it to be called. A researcher that truly studied it way back in the day, all right, and identified. So leprosy is another one, Mycobacterium leprae, that looks kind of similar like this, super hard to cultivate as well. And in some instances, lots of instances, we grow that up in an armadillo. Armadillos have a slightly lower body temperature, which is more what the leprosy would like. It prefers your extremities, fingertips, your nose, your earlobes, things like that, that are a little bit cooler than the trunk of your body, all right? And in turn, those armadillos technically are a reservoir for that. You could find lots of armadillos potentially harboring some of that, but you can get some armadillos, laboratory grade armadillos that are sterile, if you will. They don't have these organisms, and you can inoculate and see if it truly is able to grow within them. That's crazy stuff, right? And it makes me wonder who in the heck figured out the armadillo, right? I'm thinking some roadkill, right? And they stopped and collected it, and they're like, look at this. It looks like this sucker's got leprosy, right? And there we go, right? Kind of crazy. So this, technically, we're starting to transition really to think moving into the archaea, but on this tree of life with the bacteria, we can see this deeply branching bacterium clear down here, Acetothermus. And what we mean by this is super early in ancestral life, if you will, low on this tree is where we see it branching away from Luca, the last universal common ancestor, right? Those types, it's not one single sort of cell, those bacteria like organisms that ultimately gave rise really to what we start thinking over the course of evolutionary time, differentiating at this point, giving us bacteria and archaea, and at this branching point, a differentiation where we see the eukaryotes, the ancestral forms of eukaryotes progressing along. And here we find ourselves right up in here, right? So Acetothermus, a deeply branching, meaning it's diverged very long back in, phylogenetic history, ancestral history. And we can see with that, it harbors some signatures that we would classify as resembling some of those ancient types of cells that set the stage for everything else, all right? And still kicking, right? Very little change within it, all right? So shifting over, almost shifting over, Deinococcus radiodurans, this is Conan the bacterium, they say. These organisms are crazy with their capabilities of surviving things that we would say you just flat out can't live. You can't live like that, right? Super high concentrations of radioactive material. These suckers say, I'll eat that for breakfast, right? That's all fine and good. They can find them, isolate them, colonizing in the cooling ponds of a nuclear reactor, where all of those fuel rods are submerged, and it's highly, highly radioactive. If you were to fall in there, you would not come out, right? And these organisms thrive, right? There's all sorts of thoughts about how they're able to persist. And it makes you also think about, like extraterrestrial life, the ability to live in potentially higher radiation limits, maybe shows some potentials for these types of organisms. Really pretty crazy. So Sulfobus is a type of archaea, and these are able to oxidize sulfur. They, in the process of oxidizing those sulfurs, they basically produce some sulfuric acid. And in doing so, they keep it in little granules inside of themselves, little acid vesicles. Pretty impressive, I think. This, we showed a little bit with our halobacteria that are archaea, right, with the Dead Sea. This could be the Great Salt Lake, right? It could be a number of other places as well. I don't think the text actually indicates where we're at with this. I could be wrong, but I feel like as I was flipping through there, I didn't see anything that actually said where we were. I would like to imagine the Great Salt Lake, right? If you have went across the Salt Lake, the salt flats and seeing all of that, you get to a point where you can, it's sort of off in the distance, but you can see Morton Salt Factory, and you can see some of this stuff happening, right? Where they're walling off parts of the lake, and they basically rely on evaporation. They let the water evaporate out, and what's left behind are huge, looks like fields full of salt. And they in turn go in with front end loaders, scraping up huge rocks of salt, and then take it to the factory, crush it, and there's other things as they're moving through there, because it's more than just sodium chloride that are some of the salts within this that they're able to go through and get out. You can see with this, which I think is also really pretty impressive, in these fields of salt, there's some variation here, right? Where we've got more white and then some of the pink, like the Himalayan sea salt, right? This halobacteria is some that imparts these types of pigments, giving us this coloration, this pinkish tint to them. Pretty impressive, right? And able to survive, not very well, but survive in those concentrations that are basically salt crystals. All right, not a whole lot with the archaea. And as far as those guys go, really, when we think about them as like from a pathogen standpoint, at least right now, we don't have any evidence of any of them being pathogenic. We definitely may have some of them growing on us or in us, some of them potentially colonizing in our intestines. There are some people that can, eat some beans and they're all fine and good. And there are other people that can eat some beans and you know it. And so does everyone around you, because it makes you pretty gassy, all right? And really, if you get gassy by consuming beans, it's some archaea in your intestines that are ultimately lending to that condition, right? To the flatulence. And if you eat beans and you don't get gassy, you don't harbor those archaea, and in turn, don't have those situations. At least it's not the beans that are making you gassy. All right. More good stuff for 9 in the morning, right? All right. There are so many different eukaryotes as we start thinking about some of these potentials. And there are a good chunk that we really want to think about as we move through that are going to be pathogens. Some of them not, but a lot of them in this chapter, and definitely as we progress on and think disease, that's really going to be the focus, all right? There are boatloads of eukaryotic microbes that are just living in the environment, minding their own business. And then some of them that can cause some serious issues, right? There are others that we employ for our own gains, like bread or frothy beverages or the production of cheese, other sorts of fermentation processes that potentially lend to some of these eukaryotes doing some work for us, right? Or, consuming things like fungi, like eating mushrooms or something like that. Although looking at that, that's a macroscopic fruiting structure, but the hyphae, those are microscopic, all right? So all sorts of different examples as we move through. Initially, and with lots of them, I think, parasites, right? Oftentimes, really anything that's causing disease, we could say is a parasite. But when we think about really defining parasites, we think of them as Single-celled eukaryotic organisms like protists, different types of protozoal organisms. Malaria is a great example. And we'll also think about the helminths, worms, right? Those are some of the main things we think about under the umbrella of parasites, all right? But truly, if you're causing disease, you may fit under that as well, although loosely classified, all right? Malaria is truly a parasite that has caused massive issues with humanity since the dawn of humanity, right? It's plagued humans since before we called ourselves humans in the first place, all right? A super long time, all right? And there's all sorts of pretty interesting stuff to think about with that in the first place. Well, we think about things like maybe a pathogen and its host surviving for extended periods of time, millennia, right? The potential for each of these to kind of co-evolve with one another is pretty impressive. And we can see adaptations with both the pathogen, the parasite, and with the host. A battle, a struggle, trying to survive and trying to maybe manipulate one another for their own end gains. Pretty crazy, all right? So malaria, we will talk some more details with, but it is a parasite that gets into our red blood cells and replicates, causing them to explode, and those baby malaria parasites in turn infect more red blood cells, and the cycle just keeps going, all right? They are transmitted by some mosquitoes. The mosquitoes have a different stage inside of their body that's infective to us. And as that mosquito feeds on us and injects saliva to basically keep the blood flowing within the saliva, are some of these baby malaria parasites. They get inoculated into our circulation. They travel to the liver. They replicate in some liver cells. They rupture those liver cells and get into the circulation, infecting red cells, which is where they really want to be. And in turn, they go through handfuls of replications. Some of their replications generate the cells that would be infective to the mosquitoes. We call those gametocytes. They're the reproductive cells, like eggs and sperm, all right? Like it, pretty close to it, all right? And in turn, if that mosquito happens to take a blood meal and suck up some of those gametocytes, sexual reproduction happens in the gut of the mosquito. They form a zygote, they replicate, they form all of these new cells that we're seeing here, sporozoites, which in turn migrate toward the salivary gland, and now she's ready to go, right? It's always a female mosquito that takes a blood meal. They want all of those good nutrients for the eggs of the new mosquitoes, right? Male mosquitoes feed on plant juices, nectar, stuff like that. They don't feed on people, right? And lots of arthropods, it's that way. There are a few that don't care, and it doesn't matter who it is. They'll feed on you, all right? But with lots of them, it's the female that's trying to get a lot of nutrients for her eggs, and in turn takes blood meals. Crazy stuff. So this next one is a infection that's pretty common, all right? Ringworm is not a worm, but it's called ringworm, so everyone's like, oh, it's a worm, right? It's a misnomer. It was once thought, it kind of appears to be sort of ringworm-like, a worm that's causing this circle under your skin, all right? It's even got a name that signifies a worm. Tinea means worm, but it's not a worm, all right? It's a type of fungus, all right? And this is a fungus that is literally just skin deep. It lives in your dermis, doesn't penetrate deeper into the tissues. There are other fungal infections that can be much more serious, all right? Ringworm is a potential that oftentimes is something we may see in little kids, but it's a potential for pets and kids to kind of share, or adults, doesn't have to just be the kids, but to be shared between one another, maybe sort of zoonotic disease where a little puppy or kitten has some of it and then you wind up with it as well, right? Oftentimes some creams, some topical applications of some antifungal agents are applied to kill the fungus. It is something that isn't a quick fix. It takes some prolonged therapy. Athlete's foot is a similar type of fungal infection, cousin of some of the ringworm culprits. And it's a similar idea. It takes repeated applications to truly deal with it, all right? And if you don't quite think, if you don't quite follow through with it, you end up with it coming back, right? And definitely issues with that. Ooh, I love that. If you itch the ringworm and itch somewhere else on your body, can it travel? That's a great question. And my gut says yes. I think why would it not, right? If it's, pretty easily transferred from the kitten to the child, right? They've been petting it or snuggling with it, whatever it is. I would think, yeah. I mean, it's transferred from them to us or vice versa. So maybe, scratching that itch and scratching someplace else on your body just helps to inoculate that, all right? I think for sure that could be a potential, all right? Same, not the same, but like I said, athlete's foot is a similar sort of fungus, often thinking in your feet, right? But there are potentials where maybe it could get transferred to maybe some other areas of your body, maybe some areas where you don't really want that, right? If you think about putting your clothing on, right, stepping your feet through your underwear and then pulling those underwear up, puts maybe some athlete's foot where you didn't want it to be, right? My gut says, my advice to you is, if you're dealing with some athlete's foot, after you've showered and then you put on your whatever ointment onto your foot, put your socks on, then put your underwear on, then you're hopefully giving yourself a little layer of protection, all right? They do have other ointments and creams for infections in the groin, right? They call that stuff jock itch, but it's all really athlete's foot types of culprits that are lending to this. And you can get really these sorts of situations all over your body, all right? And there's a handful of different species and genera, for that matter, that can cause some of these manifestations. A few being more common for like this, and others for your feet, others that you might see maybe on your scalp or elsewhere, all right? And definitely could be transferred relatively easily, right? This picture, every time I look at it, I'm just like, man, that's awesome. Disturbing, but pretty awesome, right? I think little Giardia here, I think they are super cool, right? These little flagellated protists are kind of all over the place in the environment. In like freshwater streams are really maybe more likely, all right? These parasites live in the gut of some mammal, attaching to the intestines and absorbing nutrients. And in doing so, we mount a pretty good response against them, try to flush them out of there. We secrete a lot of mucus. We get some very mucoid diarrhea. We get malabsorption of lipids, so the stool is very fatty as well. But the diarrhea, lots of diarrhea, all right? Whether we're talking us or some other animal, all right? And it's the other animal we want to think about initially, all right? Something is infected with this out in the wilds, gets into a stream, drinks some water, maybe eats some aquatic vegetation, and while it's standing there drinking or eating, defecates into the water. The life cycle, we're just starting with this. Now these potential cysts, we're seeing what we would call a trophozoite stage or the active feeding stage, but the cyst is what's going to be infective to some other animal like ourselves or somebody else, all right? If that water is consumed and those cysts are ingested, or potentially produce gets washed with contaminated water and then consumed, right? There are multiple ways for this contamination to make its way into the body, but it's got to be the cyst stage, all right? If that cyst gets consumed, once it gets into your intestines, it exists, it hatches out, if you will, and what you see inside are these little trophozoites, the little giardia that starts attaching, feeding, growing, and then replicating, all right? And they replicate binary fission like bacteria do, splitting, dividing, and basically taking over massive amounts of real estate in your intestines, potentially covering all of the cells in, well, the duodenum is where they really like to be. We call it lamblia here in all of the intro micro courses. It's always lamblia, but Giardia has had some name changes and we apparently don't seem to care in here, all right? We change bacteria names and we want it up, right? We switch it up. That's a new addition, right? But when it comes to parasites, we're like, who cares, right? Deep down, Giardia lamblia, Giardia intestinalis, and Giardia duodenalis, 3 different species, they're all exactly the same, right? It's just the name changes that we've gone through. Intestinalis, I think, was maybe a couple of times of being called that. Duodenalis is the one that we're like, this is who it really is, all right? So there are potentials in people, all right? And it really depends on what you're presenting with. If you've got diarrhea, which you're gonna have, if you've got diarrhea, these are what you're gonna be voiding in that diuretic stool, the trophozoites, all right? But if you've got the opportunity for it to actually kind of dehydrate within the colon and make a solid stool, it stimulates those trophozoites to form the cyst stage. And like I said, that would be what's infective. So dependent upon what you present to the clinic with, fecal sample wise, is either going to be trophozoites or cysts, all right? And a single bout of diarrhea, a single diuretic stool, all right, has the potential to have 14 billion of these parasites in it. That is awesome. And I will leave you with that, with what I would like to call a true buttload, right? Or maybe step it up one extra notch, right? Buttload of parasites. Good times. Go have a glass of water.